How do engineers turn 100,000 tons of steel into a floating runway? The USS Gerald R. Ford cost $13 billion to build. One aircraft carrier devours more steel than 200 skyscrapers combined. Stay, I will show you exactly how. This machine hauls 5,000 sailors across any ocean on Earth. It hurls aircraft skyward every 45 seconds during combat operations. Without carriers, American naval power collapses overnight. The engineering challenge teeters on impossible. You must weld 100,000 tons of steel with millimeter precision. Every joint must survive 50-foot waves and hurricane-force winds. One structural failure drowns the entire ship. Only 3 shipyards on Earth can berth supercarriers. Newport News Shipbuilding in Virginia builds every American carrier. The facility devours 550 acres of industrial complexity. Each carrier demands 7 years from first steel cut to final delivery. The cost crushes the GDP of 60 nations. Block assembly erupts inside massive indoor factories, spanning football stadiums. Engineers slice the carrier into 162 separate sections called superblocks. Each superblock tips the scales at 1,200 tons when complete. Cranes rated for 1,050 tons hoist every piece with surgical precision. The flight deck sections alone consume 15,000 tons of specially hardened steel. Welders attack in teams around the clock. Every weld must survive X-ray inspection before approval. The steel climbs to 2,500 degrees Fahrenheit during welding. Cooling devours 6 hours per major joint. One failed weld cracks the entire structural grid. Quality inspectors reject 12% of initial welds. Teams re-weld every failure until perfection. The propulsion spaces demand the thickest steel armor. Bulkheads measure 8 inches thick in critical zones. Nuclear reactor compartments use specialized steel alloys costing $50,000 per ton. Radiation shielding adds another 3,000 tons of lead-lined barriers. Workers spend 4 months sealing every potential radiation path. Hull union represents the most lethal phase of construction. 2 massive cranes hoist superblocks weighing over 1,000 tons each. The Goliath crane towers 350 feet tall and rolls on railroad tracks. Positioning accuracy must hit within 2 inches of target. Wind speeds above 15 miles per hour kill all lifting operations. Assembly teams guide each superblock into position using laser alignment systems. The hull sections lock together using massive steel pins and welded connections. Engineers verify every joint using ultrasonic testing equipment. One misaligned connection spawns stress fractures throughout the entire hull. The process demands absolute precision under crushing time pressure. Welding teams seal the superblock connections with continuous penetration welds. Each major seam requires 72 hours of continuous welding. The steel climbs past 3,000 degrees during final joining. Cooling cycles devour another 48 hours before stress testing begins. Teams X-ray every inch of critical welds, using portable radiography equipment. Sparks cascade in 12-hour shifts as welders chase perfection. The completed hull tipped 65,000 tons before any systems installation. It stretches 1,092 feet from bow to stern. The flight deck spans 252 feet at maximum width. This floating foundation must support aircraft weighing 74,000 pounds each during landing operations. The deck handles simultaneous operations with 60 aircraft aboard. Island installation transforms the carrier from hull to warship. The island superstructure weighs 555 tons and climbs 150 feet above the flight deck. 2 massive cranes position the island with millimeter accuracy. The structure houses radar systems worth $2 billion. One positioning error destroys irreplaceable electronics. The island shelters the primary flight control center and navigation bridge. Air traffic controllers manage aircraft operations from 120 feet above sea level. The structure must withstand jet blast temperatures hitting 1,200 degrees Fahrenheit. Engineers install specialized blast-resistant windows and heat shields throughout the island. Cooling systems pump 50,000 gallons of chilled water through island compartments daily. Radar installation demands perfect electromagnetic isolation from ship systems. The SPY-3 radar array weighs 15 tons per antenna face. 4 antenna faces provide 360-degree surveillance coverage. Each face generates 6 megawatts of electromagnetic energy during operation. Technicians align every antenna within 0.1 degrees of specification. The radar tracks 1,000 targets simultaneously at ranges exceeding 200 miles. Catapult fitting enables the carrier to launch 80,000-pound aircraft from 0 to 165 miles per hour in 2.5 seconds. 4 electromagnetic catapults replace traditional steam systems. Each catapult generates 122 million foot-pounds of energy per launch. The electromagnetic coils weigh 120 tons per catapult system. Installation requires precise alignment within 0.5 inches, over 300-foot track lengths. The electromagnetic aircraft launch system harnesses linear motor technology adapted from high-speed trains. Copper coils create magnetic fields strong enough to accelerate 40-ton aircraft. Power systems deliver 122 megajoules of energy in under 3 seconds. The catapult track must remain perfectly straight under massive acceleration forces. Engineers use laser surveying equipment to verify track geometry after every 500 launches. Catapult testing begins with dead load sleds, weighing 80,000 pounds. Each test launch validates acceleration profiles and braking systems. The catapult must stop a 40-ton sled from 180 miles per hour in 600 feet. Brake systems absorb 45 million foot-pounds of kinetic energy per emergency stop. Steel cables rated for 200,000 pounds tension provide backup stopping power. Aircraft qualification proves every system works under combat conditions. Test pilots launch FA-18 Super Hornets at maximum takeoff weight. Each aircraft weighs 66,000 pounds fully loaded with fuel and weapons. The catapult must deliver precise acceleration regardless of aircraft weight or wind conditions. Launch intervals reach 45 seconds during qualification testing. Deck crews feel the vibration through steel plates as each aircraft rockets forward. Landing operations test the arresting gear systems that stop incoming aircraft. 4 steel cables span the landing area at precise intervals. Each cable can stop a 40-ton aircraft from 150 miles per hour in 320 feet. The arresting engines absorb 48 million foot-pounds of energy per landing. Cables must be replaced every 100 landings due to metal fatigue. Flight deck crews coordinate simultaneous launch and recovery operations. Aircraft launch from the bow catapults while others land on stern arresting cables. The choreography involves 200 sailors working within feet of jet engines, producing 44,000 pounds of thrust. One coordination error triggers aircraft collision or personnel injury. Radio discipline becomes life or death critical during flight operations. Pilots practice day and night carrier operations for 6 months before deployment. Night landings require perfect precision in complete darkness. The carrier pitches and rolls in 15-foot seas during training operations. Pilots must land within a 20-foot target area while the deck moves beneath them. Success rates below 95% ground the pilot immediately. The propulsion plant delivers 280,000 shaft horsepower to 4 bronze propellers. 2 nuclear reactors generate steam at 1,000 degrees Fahrenheit and 2,000 pounds pressure per square inch. The steam drives 4 turbines spinning at 3,600 revolutions per minute. Each propeller weighs 30 tons and measures 21 feet in diameter. The reactor compartment radiates heat that penetrates 3 decks above. Nuclear fuel loading occurs during final construction phases. Each reactor core contains 193 fuel assemblies enriched to 93% uranium-235. The fuel provides 25 years of operation without refueling. Radiation monitoring blankets every surface within the propulsion spaces. Workers wear dosimeter badges that measure radiation exposure to the microsievert. Inside this zone, not a single square inch escapes surveillance. Commissioning ceremonies mark the carrier's entry into active naval service. The ship's crew of 4,539 sailors takes official command of all systems. 6 months of sea trials prove combat readiness under operational conditions. The carrier must demonstrate launch and recovery operations in seas up to 30 feet high. Combat systems testing validates defensive capabilities against incoming missiles and aircraft. Final acceptance trials last 30 days and cover every system aboard the vessel. The Navy tests catapults, arresting gear, radar, weapons, and propulsion under maximum stress conditions. Each system must meet specification requirements before final payment to the shipbuilder. One failed system delays acceptance and costs millions in penalty fees. The completed carrier joins the fleet after 7 years of construction and 25 billion hours of labor. It represents the most complex machine ever built by human engineering. The floating city operates independently for months without resupply. Nuclear power eliminates fuel requirements for 25 years of operations. Yet every carrier requires 40 escort ships to survive in contested waters. The escorts consume more sailors than the carrier itself. Training replacement crews takes longer than building the ship. But what happens when the next generation of hypersonic missiles can outrun every defense system we've built?